So first, allow me to thank everyone for having me the guest speaker. I'm Christopher Mansour, an assistant professor of cybersecurity at Mercyhurst University in Erie, Pennsylvania, United States. A little bit about my background. I have a Bachelor's of Science in Computer and Communications Engineering from the American University of Science and Technology in Lebanon. In 2012, I attended Villanova University to pursue my master's degree in computer engineering. And in 2014, I started my PhD in engineering with focus on cybersecurity at Villanova. Graduated in 2018, where I joined my colleague Mahesh Madhumala to start the cybersecurity program at Mercyhurst University. My research interests are in securing the next generation networks, and that's the title of my talk today. So the outline of the talk, at first, of course, I'm going to start with an introduction, talking about the problems and what I'm going to address today, and then talking about the main contributions behind the research work that I've been doing, and then talk about the data plane layer solution, which is one of the solutions I propose, another solution at the firmware and operating system layer, and at the application and control layers of the software-defined networks, and then some future directions. And if I have some time, I'm going to show you a sneak peek of the latest work that was published lately in February. So let's start with an introduction. At first, computer networks constitute of three main planes of functionality: the data plane layer, the control plane layer, and the management plane layer. The data plane is the plane responsible for packet processing and forwarding, whereas the control plane is the real brain and thus represents the different protocols that are used to populate the forwarding tables of the data plane layer. And then we have the management plane, which represents the software services, such as simple network management protocol applications that are used to remotely monitor and configure the control functionality. Now, in recent modern networks, the control and the data planes are tightly coupled and embedded in the same device, and the overall network structure is decentralized. This was considered an important aspect for the design of the internet in the early days. It seemed to be the best way to guarantee the network resiliency, which was a crucial design goal. Are you talking to me, sir? Hello? Should I continue? Hello?
Yes, sir. Continue, sir.
Okay. So, in fact, this approach has been quite effective in terms of the network performance with the achievement of rapid increase of line rates and port densities. Now, modern computer networks continue to increase in their diversity, size, and complexity, and this results in the development of new protocols and communication paradigms, such as the content addressable networks that need to be deployed in order to improve the network operations. This entails the use of programmable network processors to meet such demands, in addition to a better separation between the different planes that we talked about earlier. It also entails the need of a network operating system that offers a uniform and centralized programmatic interface to the computer network. Fortunately, the advances in the performance of the general-purpose multi-core processors fulfilled this necessity by enabling the development of forwarding elements, such as switches and routers, which are based on highly parallel embedded multiprocessors system on chip. This was considered as an integral component. Networking vendors and operators can now achieve a new level of flexibility due to the use of programmable components in the data plane and in the data path. So software today becomes to be an integral part with the emergence of the software-defined networking. Now, to address the challenges in terms of complexity in management and what we call the internet ossification, the idea of programmable networks has been proposed as a way to facilitate the network evolution. The programmability simplified the deployment of new networking services leading to networks that explicitly support the process of service creation and deployment. And this programmability pushed to a better separation between the planes and to the development of the network operating system that offers a uniform and centralized programmatic interface on the network. This idea of programmable networks have also made the design and management of networks become more innovative and led to the development of software routers such as the click modular router and the newly widespread topic in computer networks or the infrastructure of the 5G networks coming forward, known as the software-defined networking. So what is software-defined networking? Software-defined network is a novel networking paradigm that facilitated the design and management of the modern computer networks. This technology didn't appear suddenly, but it is a part and a fruit of efforts that tried to make the networks more programmable. The SDN concept relies on the following main pillars. The first one is decoupling of the control and data planes, where now the control is removed from the forwarding devices, which will become simple forwarding elements. And then the second pillar is forwarding decisions are now flow-based instead of destination-based. A flow, by definition, is a sequence of packets between a source and a destination, and all of these packets of a flow receive the same identical service policies at the forwarding devices. A third pillar would be the control logic is now moved to an external entity known as the SDN controller. The latter is a software platform or a network operating system that will run on general purpose processors and will provide the necessary abstraction to facilitate the programming of forwarding devices based on a logically centralized and abstract network view. Programmable network is the fourth pillar, and this happens through software applications running on top of the network operating system. Now, therefore, we have three main layers of the SDN after all. The management layer now, which captures complex network functionality, the control layer, which acts as the kernel module that runs the applications, and the infrastructure layer, which includes the data plane layer of traditional networks. So this layered approach helps network administrators to quickly provision the network on the fly instead of manually configuring the policies. Now, if you look at this figure, on the left side, there is the traditional networks. In the traditional networks with programmability, the control plane is responsible for the configuration of the node and programming the path to be used for the data flows. Once the paths have been determined, they are pushed down to the data plane. Thus, the data forwarding is based on this control information. So in such an approach, and I'm still talking about the left side or figure A in particular, any modifications should happen through another device configuration, which means you have to go visit each and every node on the network to reconfigure it. Whereas on the right side, which is figure B, it represents the SDN view control. In the SDN view here, the control is moved out of the individual network node into a separate centralized controller. The forwarding elements, routers or switches, are now controlled by the network operating system, which collects information using the necessary API and manipulates their forwarding plane. The controller now can benefit from the network-wide visibility to optimize the flow management and implement many services. So by decoupling the control from the closed proprietary implementations of the traditional network, SDN enables us to design and distribute innovative flow handling and network control easily, and it helps much more intelligence and flexibility to the control plane. Now, what are the motivations behind the work? First, programmability has introduced a lot of vulnerabilities, and this in return could lead to attacks with disastrous effects. Adversaries can now target the network infrastructure or any virtual host connected to the network. An example of a malicious attack could be a denial of service attack. The attack code can be stored in the payload of the packet and thus will be executed by the virtual node while the packet's header is being inspected by the SDN controller. Now, the other motivation is the fact that existing intrusion prevention systems target end systems only and are insufficient against novel attacks. Also, existing software monitoring techniques are resource hungry and do not scale well. Existing hardware monitoring techniques are not powerful enough. And overall, existing monitoring techniques are not adaptive or and are not fault tolerant as well. So the main goal in my research is to ensure the correct operation of today's modern networks. And this helps in ensuring trust, reliability, fault tolerance, and resiliency for the different approaches of such networks. That is why we propose a data plane layer solution by designing a hardware monitoring technique based on the program execution flow. We also proposed an operating system firmware layer solution by designing an adaptive power monitoring technique based on the power consumption of the different processing modules. And of course, a third design at the application and control layer by designing a monitoring system that leverages the network-wide visibility with the centralized control that helps us in detecting counterfeit hosts, and malicious applications. So, before I start with the first data plane layer solution, any questions so far? All right, I'm gonna continue then. So let's start with that, with talking about this data plane layer solution. The main contribution in this particular research part lies in the design of a hardware monitoring system that can coexist with the network processor and that detects any unusual activity based on the instruction execution flow. The monitor being proposed utilizes what we call ternary content addressable memory, or the TCAM memory, in order to ensure fast detection and recovery mechanisms. The design implements what we call the concept of software diversity in order to ensure adaptivity and reliability. Moreover, the design includes an integrity checking mechanism using SHA-256 hash to check the code integrity before execution. Now, the monitoring system we present implements a security model for a secure packet processing system with the following security requirements. The first is the processor should not deviate from any normal forwarding behavior. Any intrusion attempts through the data plane should be detected and lead to a packet drop. If an intrusion was successful and was able to change the internal state of the processor, a recovery mechanism should reset the router into an equivalent functional state. And I reiterate, equivalent functional state, because that's a main concept of the design. Intrusion attempts should not lead to a denial of service due to recovery overhead. Now, in the same security context, what can an attacker do? An attacker can send abnormal packets to the network processor in order to trigger an abnormal behavior. An attacker can gain remote access to the system, or an attacker can launch a denial of service attack by resending the malicious packets over and over again. Now, in our design, the existence of the hardware monitoring detects the abnormal packets and initiates fast and secure recovery. The code integrity check we perform before any code execution eliminates the scenario of instruction memory modification. Furthermore, the integration of software diversity into our design eliminates the denial of service scenario, since a new version of the code would have been loaded and will not be affected by the same vulnerability. Furthermore, since our monitoring components are embedded in the system hardware, it is difficult for an attacker to attack both the processor and the monitor, which is usually hard to access, at the same time. Thus, this approach by design provides more security than a conventional general purpose processing system. Now, what is software diversity? Software diversity is not a new concept. It has been there forever. The idea behind it is that there are several ways to create different multiple software alternatives that are functionally the same. So we apply this concept in our design by installing n different versions of the same code. The benefits that we gain are twofold. The attacker now has to spend a considerable effort to craft different attack packets to target the particular code vulnerabilities in multiple software designs. Now, if only one version of the protocol binary is presented, the same protocol code will be reloaded during recovery. However, with the use of software diversity, we have n versions of the code, and thus the system can switch to a different version to avoid subsequent attempts to stall the system by sending the same attack packet over and over. So to explain it really quick, if you look at these two figures here, these two figures are very simple codes that copy a string from a source to destination. Both functions copies from a source to destination. However, the version 1, it just performs the exact copy. In version 2, we perform dynamic memory allocation using the malloc function, and then we copy. Version 2 is safer than version 1. But at the end of the day, both of these codes copy a string from the source to destination. Now, the figures on this slide show the implementation of software diversity. In particular, they show two different instruction sequences of the same protocol, and in this particular example, it is the IP forwarding protocol. Having different instruction sequences lead to a different monitoring graph, and I'm going to explain what a monitoring graph is in a coming slide. Furthermore, different instruction sequences means different execution flow, and this prevents recursive in-network attacks triggered by sending the same attack packet over and over. The importance of software diversity in our design is that if one version of the code was a target for an attack through a carefully crafted packet, the packet will be discarded, the processing stack will be reset, and then a new version of the code will be loaded, and this code will be functionally the same. So the same attack packet will not be able to affect the new version of the code, since carefully crafted packets take advantage of specific code vulnerabilities that will most likely not be present in the newer version of the code. And this makes such attacks harder, since the attacker now has to craft different packets to target the different versions of the code, making the attack infeasible. Now let's check the overall system. The figure here shows our design as a whole. Again, the main idea behind the monitoring system is to monitor the instruction execution flow by the packet processor and detect any deviation. So our system, as you can see, consists of two phases, an offline analysis phase and runtime monitoring phase. In the first phase, we perform an offline analysis of the protocol to be executed and then apply the concept of software diversity, generating the n different binary versions of the software. And then we generate the corresponding n compact monitoring graphs, which I'm going to explain in a coming slide. And this helps the monitor in observing the core's operation. And then for each monitoring graph, we generate a SHA-256 hash representation representing that version of the code. And then we store the value of the SHA-256 hash value at the beginning of the monitoring graph. So in terms of logic, the application binary, therefore, undergoes offline analysis to generate the monitoring graph. And then the monitoring graph will be used to verify the instruction validity, where the monitor now will ask the processor to send every instruction that is being executed to the monitor itself. And the monitor will check. If the instruction is valid, then the execution will continue normally. However, if the instruction is invalid, the packet is dropped. Now, I've been talking about the monitoring graphs generation. So during the offline analysis phase, the protocol or the application binary is analyzed, and as I said, the concept of software diversity is applied to generate the n different versions of the binary. Now, for each binary version, a compact monitoring graph is generated, and the SHA-256 is evaluated, and it is stored at the beginning of the monitoring graph. And this is used later for integrity checking, and I'm going to show how it works. Now, the monitoring graphs are basically simple state machines where each state of these states represent a specific instruction. Now, what happens exactly in offline analysis is that the binaries are divided into what we call basic blocks. The first and final instruction of each basic block are extracted and are used by the hardware monitor to verify that the instructions executed on the processor in real time are correct. The monitoring graphs are kept relatively small using compact non-deterministic finite automata as the building blocks for those state machines. The hardware implementation of the monitoring graph, as you can see in the figure, consists of a ternary content addressable memory, or the TCAM, accompanied with a BRAM memory. So why do we use a TCAM memory? We use the TCAM to store the final instruction of each of the basic block, which is usually a branch instruction, and the BRAM memory is used to store the branch target. The TCAM memory here performs what we call content matching rather than the address matching performed by standard memory cores. The content matching approach enables faster data searches that can be achieved by sequentially checking each address location in a standard memory for a particular value. The higher speed searches are achieved by using content values as the index into a database of address values. The additional ability to perform content comparison basically can be parallelized, and therefore it enables higher speed searches. So what happens here in this figure, we have the current instruction being fed to the TCAM memory, and then if there is a match, the matched address is fed to the BRAM memory, and then the BRAM memory will have a target ready. This target will be fed to a comparator that compares the target with whatever is coming from the processor to be executed next. And of course, as you can expect, if there is a match, therefore it's benign, nothing is wrong. If there is a mismatch, then there is a malicious activity. Now, the hardware monitor I'm talking about basically functions independently of the packet processor, but in parallel with it. The monitor uses as few possible resources as possible. This guarantees that an attack targeting the processor will not affect the security monitor's operation, and that the monitoring speed remains synchronized no matter what with the packet processing speed. Now, at the early stages of the runtime phase, only one of the binaries that we generate during offline analysis will be loaded to the network processor instruction memory, and its corresponding monitoring graph will be stored in the monitor memory. During runtime, the hardware monitor checks the flow of instructions being executed by the processor. If at any time it detects an abnormal operation, the processing is terminated and the recovery process is triggered. Now, during the operation, the current instruction being executed by the processor is fed to the monitor, as I showed you, particular to the TCAM memory. And as I said, the TCAM memory performs a fast search, matching its context with the current instruction. And if there's a match, no problem there. So if there's a match, the address is provided to the BRAM, and the BRAM performs a read operation, returning the next instruction to be executed. In the meanwhile, the current instruction that is being executed by the processor is stalled using a FIFO buffer for additional 2 clock cycles, where it is then compared with the returned branch address from the BRAM memory. That is where, if there is a match, there is nothing wrong. But if there is a mismatch, the next instruction is different from the one to be expected. This automatically means that there is a malicious activity, and in this scenario, the monitor sends a reset signal to the packet processor, which performs or initiates the recovery procedure. Now, talking about the recovery procedure. In the case of attack detection, the recovery process in this scenario is easy. Why? It can be achieved by simply dropping the packet that caused the failure. And this can be done without any violation, because the packet delivery in the Internet Protocol networks, as we know, is not guaranteed. Recovering from packet drops is the responsibility of the transport layer, particularly the Transmission Control Protocol, or the TCP protocol. Additionally, most of the network applications are stateless, and thus dropping partially processed packets does not lead to any inconsistencies. So, since attacks are typically based on changes in the program execution, it is necessary to reset the processing stack and as well as the instruction memory so that any potential vulnerability code is overwritten. So, to perform this recovery process, first of all, the packet buffer is cleared and the packet is dropped. The processor code is reset, and the processor stacks and registers are also reset. The instruction memory is reset, where a potentially harmful code is overwritten. The control block of the N to 1 multiplexer chooses at random which version of the processing binary will be reinstalled. And then the recovery process continues further by loading this new version of the code and its monitoring graph. During this loading phase, a hash value of the code being loaded is regenerated and compared to what we already stored during the offline analysis in the monitoring graph to check the integrity of the code. Once the recovery process is completed, the processor resumes its execution. An important aspect of this recovery process is that it happens quickly and ensures that the possibility of a denial of service attack by sending the same attack packet is not existing anymore or is eliminated. Now, in order to verify the functionality of this design, we basically implemented it on a prototype implementation of a NetFPGA first generation, or what is known as a 1 gigabit per second network FPGA, which includes a Vertex Pro FPGA. And for those of you who don't know what FPGA stands for Field Programmable Gate Array, which is basically a hardware device that allows you to design any kind of a hardware system that you need. Now, we have to choose a monitoring stream format. We have different monitoring streams. The first is the opcode. By sending to the monitor the opcode information, we can monitor the operations performed on the processor, and this indicates the functionality of the executed application. The second is the instruction address, which is basically a unique memory address used to store the instruction set. And since this address is unique, it can be used to verify the flow of instructions being executed. The third option is to use the instruction address with the instruction word. And the objective would be just to increase uniqueness. And the fourth option would be hash of any of the above. So for the prototype implementation that I'm going to talk about, we chose particularly the instruction address as the format of the monitoring stream because such a pattern uses less memory resources while making it hard for an attacker to come up with an attack code. Now, if the application code loaded at some point executes a branch instruction, as you may know, two possible outcomes could exist. The branch is taken and the next instruction to be executed is the branch target, or the branch is not taken and the next instruction to be executed is the current address plus 4. So in our design, of course, we're going to take care of all possible scenarios. Now, for an attack demonstration, we simulated it on model sim to simulate the FPGA. So this figure shows the operation of the whole system, the processor and the monitor. If you look at the figure, it shows that when the instruction 0x38 is being executed, it was fed to the TCAM element of the monitor at the same time. It took 2 clock cycles for the TCAM memory to find a match. As you can see here, the match signal was raised to 1 after 2 clock cycles. The latter is compared with the instruction being executed by the processor. Before that, the BRAM, the match address is fed to the BRAM memory, and the BRAM memory told us that the address should be the instruction to be executed next should be 0x3f. However, if you look here, the instruction that was executed after 0x38 is 0x3c, which means it is not the instruction that the monitor expected. Therefore, there is a malicious activity, and that is when the reset signal was raised and was sent to the processor in order to initiate the recovery process. So if you can notice here, the monitor detects the malicious activity after 3 clock cycles, 1, 2, and 3, and then initiates the recovery at the 4th clock cycle. Now, to show the integrity violation, we intentionally manipulated the instruction code while loaded to the processor just to check whether our monitoring graph or our monitoring system determines that the code has been manipulated. So the expected hash value that was expected from this code ends up with 5A8E1A4, and what we ended up getting is 100B6540, which is basically different from the hash value that was expected. And therefore, as you can see, a reset signal was initiated because this is a code integrity violation. Now, how about resource utilization? In terms of memory, an average processing binary file utilizes 3 BRAM 16 blocks, where each BRAM block is 16 kilobits of memory. This represents a very small percentage, which is basically considered to be 1.3% of the BRAMs existing in the NetFPGA first generation, or the 1 gigabit per second. And then if you port that design to the 10th generation FPGA, you end up with a 0.46% memory utilization. By first generation and 10th generation, I don't mean that there is 10 generations. No, there's only for so far 2 generations. It's the first one is called first because it's 1 gigabit per second. The second one is called 10th because it's 10 gigabit per second. That's the only difference. Now, in terms of TCAM memory, we needed less than 1 kilobit per monitoring graph. To be specific, we needed 672 bits. And this is considered less than 0.5% of the available resources in today's routers. So this is way too little of memory utilizations in order to achieve security. Now, of course, in order to verify that this design is effective, we decided to compare it with one of the major designs that are existing today, which is the Impress design. The Impress design stands for the Integrated Monitoring for Processor Reliability and Security, and it is a hardware-software techniques that acts at the granularity of the microinstruction. The researchers proposed such technique to detect code injection attacks and bit flips in instruction memory. In their design, they divide the binary code into blocks, and then they evaluate a checksum for each block. And then they encrypt that checksum with a secret hardware key during the loading phase, and then they re-encrypt the checksum during runtime and recalculate that value. Now, in order to implement their design, they had to modify the binary code, adding what we call a check instruction at the beginning of each basic block that basically carries the encrypted checksum for the corresponding basic block. Unlike the Impress design, the design I propose does not modify the binary code whatsoever. And then we perform offline analysis and extract a compact monitoring graph corresponding to the first and final instruction of blocks only. Additionally, we only perform the hash calculation once during the secure loading phase of the code, which also saves in memory, time, and performance. Furthermore, in the Impress design, the designers do not implement any approach to address the existence of the vulnerability in the first place. Yes, they are able to detect the existence of a vulnerability, but the vulnerability will still be there. They cannot get rid of it. So an attacker can therefore persist on resending the attack packet over and over, leading to a denial of service for legitimate processing tasks. In my approach, I implement the concept of software diversity, which replaces the vulnerable version of the code with a new secure version. And therefore, if the attacker sends the attack packet again, it will not work this time because there's a new version of the code, and therefore the attacker has to craft another packet, and therefore it defies the purpose of the attack. We also compare this design with the hardware-assisted runtime monitoring, which uses control flow for the program, control flow for each function, and it has an excessive amount of TCAM memory utilization and an excessive BRAM memory utilization for the functions. And they also stall the execution for integrity checking per block, and then they have to modify the binary by appending the hash at the end. My design, no modification to the code whatsoever. We utilize less TCAM memory and less BRAM memory. We address the vulnerability with software diversity. We utilize, as I said, less TCAM memory and BRAM memory. So in a nutshell, how would our design compare to the state of the art? In terms of additional clock cycles, we have at least we have the least amount required for attack detection and recovery. As you can see in this figure, we tested 3 different protocols on our design, on the Impress design, and on the hardware-assisted runtime monitoring design. In terms of clock cycles, we consumed the least amount of clock cycles in the 3 different protocols we tested: the CM protocol that comes with the NetFPGA, the IP forwarding protocol, and the IP security protocol. In terms of additional lines of codes required, our design does not require lines of code at all because we do not modify the code. Whereas if you look at the other designs, they do code modification. In terms of TCAM memory utilization, the Impress design here does not qualify because they don't use TCAM whatsoever. However, comparing our utilization of TCAM to the hardware assisted in the 3 protocols, we were also the least in terms of TCAM memory utilization. And that is also the case in terms of the BRAM memory utilization. As you can see, we were the least in terms of consumption. So therefore, we were able to achieve security with the least resource requirements. This finishes the first part of the design or the first solution that I am proposing. I'm gonna pause here for a minute to check with you guys if you have any question before I move on to the second solution at the OS and firmware layer. Any questions so far? Can you hear me?
Yes.
So there's no questions? Okay.
Yeah.
All right. So I'm gonna continue then. All right. So let's first start talking about this one, which is, we call it the real-time power monitoring of modular software network processors. And this is a solution that we propose at the operating system and firmware layer. So the main contributions of this is as follows. We present the design of a real-time black box novel monitoring system that detects unusual activity based on the power consumption. We measure the power at the operating system level, relating such measurements to the instructions executed, and thus ensuring that the underlying power management techniques implemented in the network processor is reflected in such measurements. We also present an analytical model to estimate the overall power consumption of a network processor based on the benchmark information of each module or process. And then we present experimental results based on a prototype implementation on click modular router. And at the end, we are able to detect malicious activity without the modification of the network processor, software, or hardware. So let's see how. So first of all, our proposed approach to monitoring the network processor is called black box monitoring, and it uses a single monitoring system that does not require any code modification to the packet processor cores. The processor core, as I said, is intact and not modified, and the power consumption is monitored across the processing modules and threads. And then the power measurements are compared with the benchmark, and this will end up providing sufficient information to detect failures or attacks in the networking processor. In terms of failures of the network processors are susceptible to two main sources, those that are caused by system errors and those that are due to malicious traffic and attacks. So errors are either the result of radiation, which could change the memory bits or cause incorrect computations, or the result of incorrect processing code. Detection of such faults involve a combination of time redundancy, that is to execute the same instruction twice on the same hardware, space redundancy, that is to execute the same instruction on a duplicate processing element, or information redundancy, such as parity check. Recovery from such errors can be achieved by resetting the processor thread and then restoring it to previous functional state. Now, attacks occur when a malformed function can trigger a fault in a vulnerable packet processor. Similarly, attacks can also modify the operation of the packet processing system. They target the network infrastructure, the control interface, or any changes in the routing behavior. Now, in both cases, errors and attacks, the power consumption of such system will change from its known benchmark norm. The monitoring system we propose targets the type of attacks that can modify the operation of the packet processing system. Modifying the operation of the packet processing system leads to a change in the processing behavior and thus its corresponding power consumption. By monitoring the resulting power consumption in real time and comparing it to the benchmark information provided by the manufacturer, deviations will be detected, alerting the existence of such attack. And again, the recovery process here is very similar to the recovery process that we discussed earlier. Therefore, we're not going to talk about the recovery process. We're going to focus only on the detection mechanism. Now, of course, let's discuss the existing techniques. Hardware monitors basically are often used in the security context and require hardware logic to be co-located with each processing element. The hardware monitors track the processor or the operation of the processor and reports unusual activities. the monitoring information is communicated through a separate interconnect to ensure the security and therefore cost of implementation. In terms of software monitors, they use a special type of software that is installed on each processing element. The monitoring information is then communicated to the central processor using the same interconnect as the processing element for moving packets and other data. And this causes performance reduction and additional cost. The performance reduction applies particularly to software monitors. Such monitors require processing resources on the network processor and thus reduce the overall system performance. Additional cost applies to the hardware monitors since they require silicon resources in the hardware chip, leaving less chip space for the elements. And this leads to an increase in the size of the chip and thus its corresponding cost. We have also management complexity. Both hardware and software monitors requires complex management. Software monitors require modification to the application binary and other additional specialized codes. And hardware monitors need a specific software to be deployed on the control processor in order to help in the configuration of the monitors. So in both of the monitor types, the requirements for the monitoring infrastructure increases linearly with the number of the processing elements. And this leads to lack of scalability in systems with thousands of processing cores. Now, in order to verify the correct operation of the network processor, the power consumption of all modules and threads need to be monitored. Additionally, a mathematical model is needed to correlate the overall system power, that is, the power that can be measured, with the power consumption provided by the benchmark. Therefore, an approach is needed here to determine the overall optimal system power of a network processor from knowing the optimal power consumption of each module provided by the benchmark. So using such information, the monitor proposed will be able to detect failure in such processors. So what happens in this analysis? The first step, the power consumption of each module inside the processor is profiled. One histogram per module depicting the distribution of the power values is generated. And the histogram is normalized to plot the probability density function of the power consumption. And then a mathematical analysis is applied and a model of the expected power distribution of the system is created. The power distribution of the system as a whole is then profiled to generate its corresponding probability density function. And then we use statistical metrics in order to compare between both the expected and the overall power distribution. And then based on this comparison, the monitor judges whether an incorrect behavior exists or not. Now it should be noted here that the power measurement should be done at the operating system level in order to take into consideration the effect and power management settings of the underlying processor's power management technique. Therefore, the power distributions obtained at this level will be accurate and therefore they can be used in the proposed design. As I said, the measurements would be at the OS level and the number of wake-ups per second, instruction executions per second, and other operating system log values and PMC counters corresponding to each of the threads or modules are measured independent from any other interrupts. In other words, only the changes that are caused by each of the processing modules corresponding to the threads will be collected, not interrupts or any other code. Also, the dynamic voltage or frequency scaling, if you are wondering, does not affect the accuracy of the measurement by any means because it acts at the level of the processor. However, our monitoring approach acts at the system level and thus it takes into consideration the dynamic voltage and frequency scaling that runs below it. So let's discuss the power estimation and of course the notation that we follow. So first, assume a processor with n processing elements, M1 to Mn. The overall functionality of the network processor is represented by the graph in this figure connecting these elements. For simplicity of the discussion, we assume that all the packets enter the processor at node M1 and they leave the processor at node Mn. Now, in order to determine the power consumption of a certain process, we denote P of Mi1, Mi2 till Mim as a path for Mi1 to Mim. And then let Pim be the probability density function of the power consumption on node MIM. The total power distribution on every path can be computed by the convolution of the power distribution on all the individual nodes in that particular path. So for path PI that has PI1, PI2, and PIN, the power of each node I1, I2 till IM all together are convoluted to find the total power distribution. Now, if path I receives an Fi percentage of the total traffic, then the probability density function is simply basically the summation from 1 to n multiplying Fi with Pi. So if a failure or an attack occurs on one of the modules and it changes its processing, the change will be reflected in the overall power that we call P-all, and it will be different from the estimated power that we call P expected. And eventually, the monitor will be able to determine that and initiate the reset signal. The difference between the two distributions can be determined using KL divergence and Earth mover's distance. Now, let's talk about the system architecture. So during the implementation of the functions of the monitor, we will calculate the power consumption of all these M modules and save them basically. And this will be based on the benchmark information, and then we will generate the corresponding probability density functions, Px. During the operation, the monitor will record the overall power consumption of the network processor based on predetermined window, generating its probability density function P-all. A decision module, as you can see here, will infer the condition of the system based on such information. If any abnormal behavior is detected, a reset signal is generated to initiate the recovery process. Now, it is important to know that for many standard processing tasks in a network processor, such as IP forwarding, IP security, encryption, decryption, there exist a lot of reference codes from manufacturers. Hence, we could easily know the power consumption of the steps in the processing thread from the benchmark that are provided by the manufacturers. Knowing the power consumption will help in determining their corresponding probability density function. Assuming we control how the modules of each tasks are allocated for each thread being executed, and assuming we know at any time the fraction of the traffic each module processes, then the expected overall power consumption of the system and its corresponding probability distribution function, P expected, can be calculated based on the discussion that I showed you earlier, the power analysis. The monitor then uses such information and compares it with the probability distribution function of the overall power consumption of the processor P-all. Any deviation from the thresholds detects a failure. So how the decision module works. The decision module has the information about the running modules, the power of each from the benchmark, and the allowed consumption deviation. It will also calculate the estimated overall power consumption of the processor. Therefore, when fed with the measured power distribution, it evaluates the KL divergence or Earth mover's distance between the estimated power and the measured power. Comparing the results with the stored benchmark thresholds, we end up having the detection of whether there is a failure or not. In the general case of a modular routers that runs protocol code, an additional module which calculates KL divergence or Earth mover's distance that are needed to detect the changes in the distribution can easily be added. The complexity of such metric is in the order of O of n, where n is the number of samples in the probability density function. This implementation is very suitable for hardware because it can be parallelized. Now, the monitor we are proposing uses a real-time sliding window in order to perform real-time monitoring. So we need to determine the optimum window size. The sliding window technique first has been used in different areas of communication systems and information theory. The window size used by the monitoring operation is predetermined ahead of time. How do we do that? Different window sizes will be tested on the overall power distribution. And for each window size tested, its corresponding average distribution will be examined against the overall benchmark distribution. The optimal window size to be used is the one that has the least deviation from the benchmark information. That is, the window size that best represents the overall power distribution. So for elaboration purposes, look at the figures here on this slide. These represent the different distributions of 4 distinct window sizes, 5, 10, 15, and 20. The figures compare the average distribution of each window with the original benchmark in 2 scenarios, the first one being IP forwarding and the second one being IP security. It is clear from the figures that the window size in the experiment did not matter here. Why? The deviation is negligible. So we decided to choose a window size of 10 in order to meet the granularity of the data that we have in hand. Now, we also have the idea of the bin size when we perform the histogram. So it should be chosen to reflect the granularity of the power values that you have in hand. So it is safe to assume that any deviation in the monitoring power distribution from the benchmark distribution will be reflected as long as the same bin size is used when comparing both. This is clear when all of the plots lined up for whatever bin size we use. Now, in order to guarantee a realistic traffic, in order to do benchmark extraction and threshold determination and testing, we used the trace file downloaded from MIT Lincoln Laboratories, and we replaced that file using TCP dump at the speed of 500 megabit per second because this is not a full duplex setup, and the analysis in the IP security focuses only on the encryption part. So in our experiment, we run the experiments without faults or attacks at first 100 times, tracing the power consumption for each iteration. And then we average all the power distributions that we measured previously to get one average distribution. This average distribution that we obtain will be used as the baseline through the rest of the coming experiments. The figure here shows 5 different normal power distributions out of the 100 iterations, as well as the average power distribution used as the baseline in the IPsec experiment. In a later step, we calculate the KL divergence we calculate the KL divergence and earth movers distance values between each of the 100 power distributions obtained previously and the average distribution chosen as the benchmark. We record these values and then we average the values of KL divergence and earth movers distance to find the average and the standard deviation. And then we set the threshold that will be used in the experiments to be the average plus or minus the standard deviation to cover for false positives and false negatives. The table here on this slide shows the average of the KL divergence and earth movers distance. It should be noted that the methods to extract the benchmark information as well as determining KL divergence and earth mover distance thresholds apply to all of the experiments that I'm going to show you in the coming slides. So let's start first with experimenting on the modular IPsec. The IPsec has 2 paths, an encryption path and a decryption path, and each with 4 modules. As I said earlier, we're going to focus only on the encryption path. The power consumption method for each of the modules comprising the IPsec cryptographic engines on this particular router and the overall power consumption of the IPsec process is represented in this figure. So as I said, there's 4 modules, module 1, 2, 3, and 4. These are the power distribution of these modules here, and this is the overall IPsec power distribution. These 2 figures represent the probability density function. The figure on the left represents the probability density function of the IPsec, and the figure on the right represents the probability density function of module 1 in particular of the IPsec. And there's a reason for that. So, to test the failure, a fault is introduced in order to cause the failure of the first module of the IPsec process after several seconds of execution. The power consumption resulting from such experiment is shown in the figure. It shows here that after the failure occurred in this module, particularly module 1, the latter module becomes inactive. As you can see, the power went down to 0. The power consumption across the module dropped to 0. The overall power consumption also dropped in the overall power consumption of the IPsec process. the same amount of module 1. So if you notice, when plotting again the probability distribution function of IPsec after failure, you can see that more values has been introduced. The same thing, if you plot the probability density function of module 1 after failure, you can see the probability of 0 values have also increased. So therefore, if you do the KL divergence and the statistical correlation, you can see that during this same window, when failure occurred, the KL divergence, which is in blue, has spiked, and the same thing happened with the Earth mover's distance. Of course, determining the thresholds, as you can see, we used the approach that I described earlier. The threshold for the Earth mover's distance was determined to be 0.6, and the threshold of the KL divergence was determined to be 1.8. Once the KL divergence in the overall process crosses the threshold, we can detect that there is a failure. The same thing applies for Earth mover's distance. Now, if we want to pinpoint the origin of the failure, we can check each module, and as you can see, they cross also the thresholds in module 1 when module 1 fails as well. Now, this is in the case of a failure. How about we talk about the higher application mechanism that we propose? I'm going to pause here again for a brief minute to check with you if you have questions, because I'm moving to a third part. Any questions from the attendees, or you can type them in the chat, I'm assuming. All right, so I'm going to continue. All right, so in the final phase of this work, we are talking now about the SDN security.
You can continue, sir.
Oh, okay, I can continue? All right.
Hello?
Yes, I'll continue, sir. Okay, so in the SDN security here, we have two sub-designs. The first is detection through power monitoring. The second is detection through system call monitoring. So let's see how it works. The main contributions behind this design is, at first, detection of counterfeit malicious virtual hosts through power monitoring. So this happens by the design of an SDN security framework detecting unusual activities in the connected hosts. We monitor the power consumption of each of the connected hosts at the operating system layer, and then we provide experimental measurement results from a prototype proof of concept implementation with Docker containers serving as virtual hosts in an SDN framework based on Mininet emulator and Open vSwitch. The second main contribution is the detection of malicious applications through system calls monitoring. And this happens by the design of an SDN security mechanism that detects malicious applications by periodically monitoring the system calls of those applications. And then we show experimental measurement results from prototype proof of concept implementation, again, using SDN framework based on Mininet emulator and Open vSwitch. So let's get started. Let's get started first with the counterfeit host detection. So the use of counterfeit devices in modern computer networks is very dangerous, and it poses a real problem. Counterfeit hosts inside a modern network may lead to the injection of faulty and malicious data that can corrupt services and threaten the integrity and trustworthiness of the information that is being exchanged. A counterfeit malicious host can be the single point of entry to the network, giving an attacker an easy access to the networking infrastructure. Malicious code can be carefully inserted between legitimate lines of code in order to be executed later, allowing attackers to gain access to systems and disclose information. However, when counterfeit hosts execute malicious activity, their corresponding processing characteristics and PMC counters, what is known as performance monitoring counters, will vary. This will be reflected in the power consumption of such hosts. Furthermore, when a failure or a malicious activity targets a particular virtual host, the power consumption of that particular host will deviate from its normal distribution. Hence, if we continuously check the power consumption of the virtual host in real time, we end up being able to detect failures or unusual activities. So let's discuss the virtual host power analysis. The virtual host's power is extracted at the operating system and profiled after checking the processing characteristics such as wake-ups per second, CPU cycles, and other performance counters. The power values collected are normalized in order to unify the bin size. Now, one histogram per virtual host that depicts the distribution of the power of that host is generated. The histogram is then normalized in order to plot the probability density function of the normalized power, and the power consumption of the virtual host is monitored in real time, and the corresponding probability density function is also generated. The application and controller now at the SDN layer, at the application layer, I mean, will statistically correlate the two distributions and determine any deviation. And based on this outcome of this statistical correlation, a malicious activity or a failure can be detected and flagged. So let's talk about the architecture and operation. The control logic is logically centralized and leverages the network-wide visibility of the network in order to monitor the power consumption of the multiple virtual hosts that are being connected. So as you can see, each virtual host is basically a Docker container virtually connected to an Open vSwitch or OVS switch, and then provides the necessary API in order to be monitored and controlled. The Open vSwitch provides the necessary forwarding layer abstraction to the controller that and abstracting the connected hosts basically connected to it. Therefore, the controller now will be able to collect the processing characteristics and power consumption in real time for each and every virtual host connected to the network. Therefore, with the statistical correlation, the controller will be able to determine the existence of a malicious activity and notify the network operator. So how does it work? As you can see, the virtual host provides the details. We calculate the power consumption. We analyze it based on what I discussed earlier, normalize it, and do the PDF extraction, and then give it to the controller's decision module. That module already has the expected probability distribution function. It compares them, and based on that, determines the outcome, whether there is a malicious activity or a failure. Now, again, I'm not going to go through the process of optimum window size determination. Again, as you can see, they lined up regarding the bin size that we carefully chose and everything that we already done. So these are basically the same steps that we follow at the firmware operating system layer to determine the optimum window size. We used it here as well to perform optimum window size. And as you can see, the powers aligned. So any window size and any bin size works for us. Now, for a benchmark extraction, we follow the following steps. We run the experiment 300 times without faults or attacks. In each iteration, we extract the power consumption of the virtual host under test, and then we average all the measured power distributions to get one average distribution. And then this resulting distribution will be used as the baseline benchmark reference for the monitoring process throughout the experiments. And then we calculate the KL divergence and earth movers distance values between each of the 300 power distributions that we obtained. And then we average the values, finding the standard deviation, and then we set the threshold that will be used later in the experiments to be the average plus or minus the standard deviation to cover for the false negatives. And guess what? If you may have noticed, we used the exact same procedures that we followed in the benchmark extraction in the firmware operating system layer as well. So this slide here shows the details of the benchmark extraction and the average KL divergence and earth mover distance values. So as you can see, we have 5 sets of data out of the 300, and then compared to the average baseline. And as we said, the average KL divergence was determined to be 3.8, and the average earth movers distance was determined to be 11.5. Of course, there's standard deviation, and based on that, we can determine the threshold to be used. Now, notice the title of this slide. I'm calling it binary classification detection algorithm, and there's a reason that I'm going to talk about at the end. However, for now, it's a detection algorithm, and it's called binary classification. So during the software-defined networking setup, the controller will extract or save the benchmark information of all the virtual hosts that are connected. That is, for every virtual host being added to the SDN framework, the controller will have a baseline power consumption distribution. During runtime, the controller will leverage the abstraction provided by the Open vSwitch and collect the power characteristics of the virtual host to be inspected in real time using the necessary APIs. At the same time, the controller will generate its corresponding probability density function as we discussed earlier, and then performs statistical correlations according to this algorithm. So when it does the KL divergence calculation and earth mover distance calculation, if they cross the threshold, an alert is said to be true. Now, in order to verify the functionality of the design proposed, we present a prototype implementation as a proof of concept, of course, based on an SDN framework consisting of an Open vSwitch to control the virtual hosts. And the Open vSwitch is a virtual switch that resides on the server and is used to connect the virtual hosts. The virtual hosts are Docker containers of Ubuntu Trusted Distribution, and they utilize Docker's daemon RESTful API. Now, we use the RESTful API in order to communicate with the engine and extract the processing characteristics. The main characteristics of interest in our scenario are the structure CPU stats and pre-CPU stats. The pre-CPU stat structure basically represents the CPU metrics from a previous tick before the monitoring, which means the initial CPU metric just before the monitoring process. The CPU stats, however, is the structure that represents the CPU metrics at this particular instant in time when the measurement was collected. Now, these two structures with their attributes can be used in calculating the percentage of CPU utilization according to the following equation. So the percentage of CPU is the delta total processor usage divided by the delta total system usage multiplied by n multiplied by 100. So what is n? N is the number of cores of the machine that these Docker containers are running on. In my particular scenario, it was 8 because I had 8 cores machine. Now, the delta processor usage basically is calculated as follows. We subtract from the structure pre-CPU status the total usage from the total usage of the CPU status to find the delta total processor usage. The delta total system usage is basically the total system usage in the pre-CPU structure subtracted from the total system usage from the CPU status structure. So whatever is before is subtracted from whatever is next at the measurement. And then we perform this equation in order to calculate the percentage of CPU utilization. Now, how about the detection rate and false negatives? Before I show you how we do that, it is impossible to determine the rate of attacks or failures in the network. One way to determine the efficiency of the proposed design is to estimate the detection rate. So we randomly introduced attacks with power profiles closely above the benchmark power, and we later counted the number of lagged incidents. The detection rate will be basically as simple as the ratio of the number of lagged attacks to the actual number of attacks that we introduced. In the prototype implementation we presented, we have a detection rate of 96.3%. Now, additionally, in order to determine the false negative rate, we conducted the experiment 300 times, 50 times of which were randomly introduced active attacks. We later counted the number of lagged incidents. The false negative rate basically is the ratio described in the following equation, which is basically 1 minus the detection rate multiplied by the actual attacks divided by the non-flagged incidents. In our particular prototype implementation, the false negative rate was determined to be 0.7%. This low rate is appealing because that's where lies the real danger of a potential attack going undetected. So let's first start with failure detection. We look at virtual host 1. As you can see, this is the probability density function of the virtual host. Actually, it's the opposite, I'm sorry. This is the average power consumption of the virtual host, and this is its corresponding probability density function. So this is the normal behavior of the virtual host. Now, we maliciously or intentionally introduce a failure to the virtual host during this time window here. And as you can see, this failure was reflected in the power consumption dropping in the virtual host and was also reflected in the probability distribution function. Again, I'm sorry, I flipped the titles. This should be the probability distribution function, and this should be the average power consumption. Now, if we do the statistical correlation using KL divergence and Earth mover's distance that we used earlier, as you can see, we have them plotted here. The threshold was determined to be 3.8 for the KL divergence values and 18.8 for the Earth mover's distance. So during real-time monitoring, a KL divergence value greater than 3.8 will determine an abnormal behavior of the virtual host. Similarly, an Earth mover's distance value greater than 18.8 will basically determine a malicious activity or something wrong in virtual host, number one in particular here. So whenever you are doing this calculation in real time, once it crosses the threshold, the algorithm will flag the incident and alerts the network operator. Now, how about attack detection? So in this experiment, we executed a denial of service attacks on the virtual host in order to check whether such attacks are detected. The power consumption, as you can see during the denial of service, increased, and it is reflected in this figure here. And of course, the probability density function of the virtual host after the attack is also represented in this figure. And guess what? We're going to do also KL divergence and Earth mover's distance to check whether this is good or not. So as you can see, the same threshold values here apply. And as you can see in real time, once we have an Earth mover's distance above the threshold, there is an attack. And once we have KL divergence above the threshold, we also determine that there is an attack. Therefore, the proposed prototype implementation was able to detect an attack scenario on the virtual host. So this is part or subpart one of the SDN design. Now, how about the malicious applications in SDN? So an appealing benefit of SDN is the ability to develop plethora of applications. And these applications basically provide lots of services to facilitate the different use cases. Such applications include sophisticated code base that is prone to a variety of bugs and vulnerabilities, and therefore exposes the SDN network to malicious activities. And with the emergence of SDN application stores, such as HP's SDN store, the SDN application that are being deployed are most likely to be provided with limited testing and security checking from third-party entities. Therefore, attackers now can exploit the vulnerabilities existing in such applications, turning them into malicious applications to be used in order to gain access to the network resources and manipulate the network operation. Malicious applications can sniff the network topology or even tap into the network, disclosing confidential information to the attacker's site, or can even modify a message that is supposed to be processed by another running application, causing the latter to throw an unexpected exception. The reason such applications can be installed is that there is no guideline about malicious behaviors of the SDN application. So the reason we need a monitor, or the motivation behind needing such monitors, is the fact that most SDN controllers do not adopt an inspection mechanism for SDN applications before executing them. Furthermore, the monolithic design of the SDN controllers implies that a failure of any of the applications can render the entire control plane unavailable, which is particularly dangerous and can cause a complete network shutdown. So, system calls to the rescue. System calls basically are used by the applications in order to request services from the operating system. Each application has a specific number and order of system calls that it utilizes when performing its particular operation or task. So capturing and monitoring such information will definitely help in determining the existence of malicious and faulty applications. System calls monitoring is very useful in detecting malicious applications, specifically those that are exploited to perform code injection attacks. The exploited application will utilize the system call in a different manner than what is expected. The variation of system calls might be reflected with new calls, that is, new type of calls that have never been used before, or it could be reflected by additional number of particular existing function calls, or a different order of the calls. Hence, the use of an additional function call, which is a call that has been never used before, is a clear indication of a malicious activity. So when an application starts to act maliciously, the system call's characteristics utilized will vary from the normal expected behavior. Additional type of system calls might exist, and the frequency of each type also will change. Therefore, periodically monitoring the system calls of the SDN application will definitely help in detecting malicious activities. So let's see how. Let's look at the system architecture. The application to be installed basically is first analyzed in order to extract the type of the system calls utilized when running a particular task and their corresponding frequency. Such information will be used by the controller as a baseline in order to determine possible deviations during runtime and therefore detecting malicious activities. In real time, the controller will periodically poll the application while running a particular task and then will extract the type and frequency of the system calls involved and then compare such information with the previously extracted baseline information to determine the existence of a malicious activity. So, as you see, during offline, application goes through static analysis, the sequence of calls used by that application and the number of calls are picked up and they are provided to the comparison module. During runtime, the same thing happens. The system calls are extracted, sequence of calls and numbers of calls are extracted, and they are collected. The actual ones are collected during runtime. They are compared, and then there's an alert if there's not a match. How does it work? So of course, we have to extract a benchmark. So to do that, we run the experiment 100 different times without attacks. And then we collect the different types of system calls and their corresponding frequencies at each iteration. And then for each system call type T, we call the average mu T and the standard deviation delta T. So we calculate those average and standard deviation for each type of the system call. So if you have 10 types, you end up having 10 average standard deviations. And the average of the system call type will be used as a baseline, and the standard deviation will be used as a threshold. So how does it work? During runtime, the system calls of the monitored application and the corresponding frequencies of that system call are collected. For each type, the deviation from the mean, that is def-t, the absolute value of ft frequency subtracted, or the mean subtracted from the frequency, is calculated and compared to the standard deviation delta t. So basically, we have the mean, we have the standard deviation, we collect the frequency and its type, we calculate the deviation from the mean, and we check, is the deviation greater than the standard deviation? If yes, there is an alert. So in the particular example, as you can see, when we run this particular example, we end up having the system calls write, select, mmap, read, and open. We had 123,691 writes and 13,408 selects, 12 mmaps, and read. If we do that, if we calculate the deviation from the mean, we end up having a large deviation bigger than the standard deviation here, and there is no deviation for the last three functions or the last three system calls. It is enough for one system call to deviate from the mean in order to determine that there is a malicious activity or there is a malicious application. So we set the alert to true. Now, to determine the failure rate, we run the experiment n, or whatever we call it. The reason we call it an n is it is a normal running phase. we run it 100 times without malicious activity. For each type of the calls, we calculate the number of iterations of those whose deviation exceeded the standard deviation, and we calculate NT1, which is the number of iterations whose deviation fell below the standard deviation. Then we run the experiment again 100 different times, but with attacks all times. And we also calculate the number of iterations of deviation exceed delta t or the standard deviation, and we calculate NT2, which is the number of iterations whose deviation fell below the standard deviation. The false negative is calculated according to the following equation. NT2, which is the number of iterations whose deviation fell below the standard deviation, divided by NT1 plus NT2. The false negative rate of this particular algorithm or prototype implementation turned out to be 0.83%. So I'm going to conclude the talk and provide some future directions, and as I promised, a sneak peek of the latest research work that was published this past February in a conference. So, as a conclusion, the architecture of the next generation networks is going to be based on modular networking functions that could be deployed and scaled on demand to effectively accommodate the different use cases. The building block of such transformation is the advances in the performance of hardware compared with the growing availability of open source software solutions. This latter softwareization has introduced a lot of vulnerabilities that are particularly problematic at the level of the networking infrastructure. In this research, the reliability, security, and trust for modern computer networks were addressed by designing and implementing a multi-layer security mechanism which addresses the data plane layer security, the operating system layer security, and the application and control layer security. In the future, the application layer and control layer designs can be improved to become smarter and robust. This can be achieved by the introduction of machine learning. Machine learning can be utilized in two different ways: attack prediction or application classifier. Utilizing machine learning can help in outsmarting malware and therefore perform attack prediction. The design can predict the likelihood of a malicious application by analyzing the sequence and frequency of the different system calls. Furthermore, machine learning can be used to build a robust classifier with high accuracy. Such classifier can be used in order to declassify the applications that are vulnerable to become malicious from those that are not, but by basically performing behavioral analysis of each application. So as you can see, there is a sneak peek here, and this is what I'm going to show you later in the coming slide. So another important aspect here is to answer the following questions. The questions that I want to answer are: what features can be extracted and used to build a resilient and reliable infrastructure? This could be a research ongoing. Another research ongoing is: what is better machine learning approach, supervised or unsupervised? And what's the optimal way to implement machine learning, software or hardware? And how we can address the false positives most efficiently. And that's where I can show you the results of February. So that's the sneak peek of the latest work. That's going to start right now. So I'm answering the last question. We were able to do that last February. So we started with the supervised learning process. We went back to the power consumption, and we ended up collecting 1,000 different power measurement sets for which we know their corresponding class. By that we mean, we know whether that data set is an attack or not. Half of these power measurements correspond to normal behavior, and the other half is collected after performing a random malicious activity. We measure and we made sure that the information included in the dataset was labeled correctly. We used a procedure known as a holdout, which works by setting aside some proportion of the pre-labeled data for training and the rest for testing. And in our proof of concept implementation, we use a particular implementation known as cross-validation. And we hold out 20% of the dataset for evaluation and the rest for training. So as you can see, we have the power samples of malicious activity, power samples of normal activity go into the machine learning training phase. Then we end up generating a model. We have testing data set using cross-validation holdout technique, and we have classification results, which is basically determining whether it is malicious or benign. Now, we implemented a multimodal training. So this includes a democratic style learning with several models in semi-supervised learning mode. Different models basically help diversify the inherent inductive biases. At each iteration, if n-1 models agree on a label for a previously unlabeled data point, it is then added to the nth model as training data. The final prediction can be made with a majority voting scheme, which I'm going to explain soon. The classifiers chosen in the multimodal are support vector machine, KNN or nearest neighbor classifier, and naive Bayes. And of course, for all the models, we calculate the accuracy as following. The accuracy is calculated as the true positive plus true negative divided by true positive added to true negative added to false positive added to false negative. So let's start with the support vector machine. It is used to produce a probabilistic binary classification model to determine whether the input power consumption trace belongs to a malicious activity or to a normal one. The confusion matrix for the support vector machine is as follows. We have 100% true positive, 0% false positive, 3.3% false negative, and 96.66% true negative. The accuracy, based on the formula I just showed you earlier, is 98.33%. Comes next, k-nearest neighbor. Since we have two classes only, benign and malicious, an odd value of k is recommended to avoid the tied votes in the majority voting. So we chose k to be 5. The input power measurement data set can be classified by a majority vote of 5 of its neighbors. Again, the confusion matrix resulted in a 100% true positive rate, 0% false positive rate, 6.66% false negative rate, and 93.333% true negative. The accuracy is 96.667%. Now we have the naive Bayes classifier, which is basically a classifier based on applying the Bayes theorem. One advantage of using the naive Bayes classifier is such a classification technique works well in the case of limited data sets, which we had that problem. The confusion matrix basically had a true positive of 99.2593%, a false positive of 0.7407%, a 0% false negative, and the 100% true negative. The accuracy of the naive Bayes is 99.62%. We didn't stop there. Looking at the previous confusion matrices, it becomes evident that none of the algorithms alone perform ideally. Some of them have a low false positive rate and a high false negative rate, like the k-nearest neighbor and the support vector machine model, where others have a low false negative rate and a high false positive rate, like the naive Bayes model. So to address this issue, we keep both the false positives and false negative rates at low percentages, we use what we call the majority voting decision fusion technique. This technique consolidates the decision provided by the classifiers that form the multi-classifier based system. The proof of concept security framework that we implement consists of the binary classifier that I showed you earlier, and I told you to remember this at the end, the SVM classifier, the k-nearest neighbor classifier, and the naive Bayes. In our scenario, as you noticed, not all the classifiers showed similar accuracy rates and performed well. Therefore, we use what is known as the majority voting decision fusion with weights in order to determine more accurately whether a malicious activity or a counterfeit host exists in the SDN framework. Now, since the naive Bayes algorithm proved to be the best in terms of accuracy, and in order to avoid a tie in voting, because we have 4 algorithms, we doubled the weight of the naive Bayes. So the figure on this slide basically represents the majority voting system architecture in order to determine whether the collected power measurements correspond to a malicious activity or not. So as its name states, the outcome is based on the majority of the decisions. Hence, whichever class gets 3, so if you notice, SVM has a weight of 1, KNN has a weight of 1, naive Bayes, which performed the best, has a weight of 2, and binary classification has a weight of 1. The total is 5. Whichever ends up getting 3 out of 5 votes, taking into consideration the naive Bayes counting 2, is considered the right class, whether it was malicious or benign. Testing the majority based system on 1,000 new samples with known classes showed a significant improvement in the overall false positive and false negative rates. The false positive is now 1%, while the false negative rate is at 0.3%. As expected from the probability theory behind majority voting, the accuracy of the majority voting scheme far exceeds the accuracy of each individual classifier, achieving an accuracy rate of 99.99%. Thank you so much for having me as a guest speaker today. If you have any questions or additional information, or seek additional information, feel free to reach out to me anytime at cmansour@mercyhurst.edu, or you can visit my website, christophermansour.com. There is a place where you can drop me a line, and I will get back to you, of course. Now, of course, if you have any questions for today, please feel free to send them in the chat or ask, and I'm gonna be available to answer any question you may have. Okay, so I can see some of you have posted a question in the chat. What is the difference between router and click modular router? So the click modular router is a software router that is basically implemented in a C-like code language, and they basically code modules, and therefore for a particular functionality, you can have different modules separately chained together in order to implement a particular function in that particular router. Any other questions? Right, I'm not sure if you are still there, and I know that my colleague was not able to join because of the limited number of attendees or something. So we ended up half an hour earlier than expected.
Sir, sorry for the interruption.
Go ahead.
Sir, we are the organizers. Just a note to the audience here. Audience, now you can raise your doubts and can get clarified with speakers through a chat box.
I didn't hear you well, sir. Is there a question or what?
Sir, good morning.
Good morning.
Yes, sir, I am the HOD of EC of this Nirula College. Sir, I had a doubt, sir.
Nice to meet you. Yeah, what's the question? You go ahead.
Yeah, sir, which type of kernel you used while performing SVM, sir?
What's that? Sorry?
SVM, support, when you're applying support vector mission, I think we have many kernels for support vector mission. To apply support vector mission like linear, exponential, quadratic, and radial basis kernels. Which type of kernel you used while performing classification using SVM, sir?
I didn't go in details on the SVM, to be honest with you. Okay. I just used the SVM model that is implemented by default in MATLAB. So I just used that implementation to perform, because my objective is not to invest in changing the classifiers. It's just on using them to help me optimize the false positive and false negative rate.
Yes, I know that if you use radial basis, as it has broad dimensionality and exponentiality, it can improve the true positives in any classification. Hence, I'm asking what type of classifier you used.
Oh, thanks for the feedback. That's great then. I might try to resimulate it then and check that. To be honest, as I said, I used the default implementation. I did not go in details about the machine learning whatsoever.
Okay.
Sure.
Thank you so much, sir. Thank you for your wonderful message, sir. It's been long time, 1.5 hours. Thank you so much, sir, for your wonderful message. And many people are satisfied with your message. Thank you for your kind acceptance also.
You're welcome anytime.
Okay, thank you so much, sir.
I can see that this session is being recorded. If you don't mind, can I get a link to that session to watch it later for my own records?
Sure.
Sure,
Yes.
sir, definitely.
Yes.
Sure,
Please.
sir. Sure.
Thank you so much.
Thank you, sir. Thank you.
All right. Have a good day.
Sir, we are very much thankful to you for being in the session and sharing your valuable knowledge in the webinar. And I hope all the audience got a fair knowledge with your keynote. Any one of the audience have doubts can raise them in the chat box. Anyone else? Yeah, the session continues. We'll have another speaker today who is a professional in cybersecurity, Dr. Mahesh. And please, all the audience, please wait for the session. And Dr. Christopher, sir, thank you for joining here and accepting your request and sharing your knowledge. Thank you so much, sir.
Okay, so I should leave. You want me to leave?
Yes, sir. Yes, sir.
All right, I will
Dr. Mahesh
leave.
will join, sir.
Okay, got it. I will leave now.
Right.
All right.
Thank you, sir.
Sir, thank you so much. Thank you
Sure.
very much, sir.
You're welcome. I just want to see how can I leave.
Yeah.
You can. I think you can kick me out. I can't find the end call, to be honest with you. I can't see where I can leave the call. Okay.